A soldering iron looks like one of the simplest tools in manufacturing, a heated tip, a roll of solder. But in modern electronics, that tiny contact point can decide whether a missile guidance board survives vibration, whether a medical device keeps working inside a patient, or whether a telecom system fails in the field years later. For decades, hand soldering was treated as a craft problem. Metcal helped turn it into a physics problem, and that shift changed the economics, the reliability, and even the language of electronics assembly. The question at the center of this story is simple. How did a small Silicon Valley company reinvent a century-old tool by heating metal with radio frequency energy instead of just making a wire glow hot? In the age of miniaturization, failure rarely begins with the glossy outside of a product. It begins at the joint. A solder joint is the microscopic metal bond that connects a component to a circuit board. If that bond is weak, cracked, overheated, or poorly formed, the device may work at first and fail later. A US defense reliability study on surface mount technology described solder joint fatigue, manufacturing anomalies, and inadequate process control as central reliability problems, especially as designs became denser and less forgiving. In plain English, the parts kept getting smaller and the margin for sloppy heating kept shrinking. That was the market Metcal walked into. The company traces its beginnings to 1982 in Silicon Valley, where it started as a scientific startup focused on building better soldering stations for electronics manufacturing and repair. Not a consumer gadget brand, not a broad industrial conglomerate. A specialist, its ambition was narrow and severe. Solve one of the most deceptively difficult problems on the electronics bench. How do you put exactly the right amount of heat into a joint, quickly enough to work, gently enough to avoid damage, and consistently enough that a factory can trust the result? What made Metcal unusual is that it did not begin by polishing the conventional soldering iron. It began by attacking the assumptions behind it. Traditional adjustable temperature resistive systems work by running current through a resistive heating element, measuring temperature with a sensor, and using control circuitry to chase a set point. That can work well, but Metcal's own technical literature lays out the weaknesses clearly. Resistive systems can overshoot temperature, need calibration to maintain set point accuracy, and often lose performance as the thermal load gets larger. In simple words, the harder the joint, the more a normal iron can struggle right when precision matters most. By the mid-1980s, the patent trail shows what Metcal's engineers were really building. In 1986, a Metcal patent by Robert R. Clapier and Stephen J. Smith described a constant current radio frequency generator designed to drive difficult loads without damaging the amplifier. That sounds abstract, but it was essential. If you want to heat a soldering tip with RF power instead of a simple resistive element, you first need a power architecture stable enough to handle the ugly realities of a production tool. Metcal was not just designing tips, it was designing an RF power ecosystem for the bench. Then came the heater itself. In a 1988 Metcal patent, inventor Philip S. Carter described an auto-regulating electric heater that solved a practical but serious problem. Older designs could waste energy in the handle instead of the tip, making the tool inefficient and unpleasant to use. In plain English, that is the opposite of what you want. A soldering iron should put heat into the joint, not into the operator's hand. Carter's work increased impedance and improved efficiency, so the energy went where it belonged. That sounds like an engineering refinement. In practice, it was part of the foundation for a different class of tool. A year later, Metcal patented one of the ideas that would define the brand. In 1989, Mark J. Cowell's cartridge soldering iron patent described a replaceable tip cartridge system with temperature auto-regulation, minimal heat transfer into the handle, and startup times as low as 7 seconds after a cartridge change. That mattered for two reasons. First, it puts the heating technology near the business end of the tool, where performance actually counts. Second, it made temperature and tip geometry part of a swappable cartridge system. Metcal was not selling a hot stick anymore, it was selling a modular thermal process. That same year, another Metcal patent from Cowell, Kevin Ladd, and Philip S. Carter Jr. pushed the heater closer to the tip to improve performance under heavy thermal loads. The problem they identified was blunt. When the tip itself was cooled by a hard job, earlier designs took longer to recover. The solution was to bring the self-regulating heater closer to the working surface. Again, the logic was not cosmetic, it was thermodynamic. The closer the heating action was to the joint, the faster the tool could respond when the board tried to steal that heat away. By 1992, Metcal engineers Mark J. Cowell and Stephen A. patenting ways to adapt Curie-point self-regulating heaters for lower operating frequencies while preserving performance. That detail matters because it shows a company still tuning the architecture, not just protecting a finished product. Metcal's invention was not one patent and one lucky launch. It was a sequence of engineering decisions around power delivery, heater geometry, thermal feedback, and manufacturability. The brand was built the hard way, one constraint at a time. The concept that tied all of this together became Metcal's signature, SmartHeat. It sounds like branding, but underneath it was a very specific physical trick. Metcal's system used a high-frequency alternating current power supply and a specially constructed heater. The current first flowed through a conductive copper core, then, because of a phenomenon called the skin effect, concentrated near the outer surface where a magnetic layer had higher resistance and heated rapidly. When that outer layer reached its Curie-point, it lost its magnetic properties. Once that happened, the heating mechanism backed off automatically. As the tip cooled, magnetism returned, and the cycle started again. The result was a heater that regulated its own temperature. Metcal's own phrase was the simplest explanation: the heater is the sensor. That is the heart of why Metcal felt different in the hand and on the line. A conventional iron measures temperature, then adjusts. Metcal's SmartHeat system was built so the heating material itself changed behavior at the target temperature. No separate calibration ritual, no elaborate external sensing loop at the point of heat generation, no large overshoot as a normal part of operation. In plain English, Metcal tried to make the laws of metallurgy do the controlling. That is a very Silicon Valley kind of move. Replace management with architecture. The second piece of the magic was induction. Metcal's white paper explains the distinction cleanly. Inductive soldering uses alternating current through a coil to create an alternating magnetic field around a ferromagnetic material. That produces heat through hysteresis and eddy current losses. The details sound academic until you translate them into factory language. Fast heat up, fast recovery, strong performance on medium and large thermal loads, less waiting for the tip to catch up, less dwelling on a pad while the board sinks heat away, less accidental damage to surrounding components. And that is where Metcal's technical story met the market. Electronics assembly in the 1980s and 1990s was moving toward denser boards, finer pitch parts, surface mount packages, and harsher reliability demands. The old benchmark for a soldering iron had been simple: does it get hot enough? Metcal changed the benchmark to something more industrial. Does it recover fast enough, hold temperature tightly enough, and produce repeatable results under real thermal loads? In sectors like aerospace, medical devices, automotive, military, and telecom, that difference was not academic. It was the difference between a tool and a process control device. Metcal's own application material makes the value proposition especially clear in military-grade and high thermal mass RF boards. These boards are designed with ground planes and heat spreaders that pull heat away from the joint. That is good for the product in operation. It is bad for the person trying to solder it. Metcal argued that many conventional systems simply do not have the reserve power to keep tip temperature stable when those boards start sinking heat. Inductive heating, by contrast, offered faster initial heat up, shorter dwell time, and faster recovery. In plain English, Metcal was strong where other irons felt weak, on the jobs that punished the tool. That advantage eventually hardened into a flagship platform. By the late 1990s, the MX500 system was already in the field, as shown by Metcal manuals, copyrighted in 1998. In its later official datasheet, Metcal would call the MX500 a bench top icon. The modernized system kept what made the platform famous: dual switchable ports, SmartHeat cartridges, 40 watts maximum output, and a 13.56 MHz RF output frequency. That number matters. It is not a metaphorical radio frequency. It is literally RF power on the bench. By then, the human story had changed. Metcal was no longer just a Menlo Park startup defined by patents and engineers. In 1996, OK International acquired Metcal. The terms were not disclosed publicly in the sources available today, but the strategic meaning is clear. A technology-led niche innovator had become important enough to be folded into a larger benchtop equipment business. For Metcal, that meant scale, channels, and a broader manufacturing platform. For OK, it meant owning a differentiated soldering technology with strong credibility in high-reliability work. The next corporate turn came in November 2000, when Dover Corporation acquired OK International. Dover said OK's calendar year 2000 sales would be approximately $100 million and described the company as a global maker of professional tools and equipment for electronics, telecommunications, and general manufacturing. It also listed Metcal soldering and desoldering stations among OK's core product lines, alongside BGA rework systems, dispensing systems, fume extraction, ESD instruments, and wire wrapping tools. In other words, the small startup technology from 1982 had been absorbed into a far larger industrial stack. That usually marks the point where a story loses its edge. Many specialist brands get bought, rationalized, and flattened into a catalog. Metcal did not entirely avoid that danger. The hand soldering market became more crowded, more price-sensitive, and more feature-driven. Resistive systems improved. Competing brands fought on ergonomics, user interfaces, cartridge ecosystems, and price. Even inside Metcal's own orbit, the benchmark had moved. The challenge was no longer just proving that RF heating worked. It was proving that Metcal could still define the next category after SmartHeat. Subscribe for more stories on the overlooked companies and tools that shaped modern manufacturing.